Thank you, Professor Karimi. Now I share my screen presentation. So I think it's good, right?
Yes,
it's good. Thank you again, Professor Karimi, for this webinar and OIE publishing services. And today I will give you some. I will give you a presentation about autonomous driving technologies for hybrid electric vehicle energy savings. Let me give a little bit about myself. So I am an assistant professor of mechanical engineering here at Tarsus University. I do research in control system area, ranging from robust control to adaptive control, as well as predictive control design. So my application area is on autonomous and electric vehicles development. So I apply the controlled techniques, new control techniques in this trust area. As the name states, I will start with the definition of an autonomous car. So as we can see, autonomous car is capable of sensing its environment and operating without human involvement. In this regard, a human passenger is not required to take control of the car at any time. Autonomous car, as seen here, can go anywhere like a traditional car does. For that, it has some sort of features. So in terms of driving systems, which is also called as driving assistance systems, autonomous cars are equipped with variety of them. I can first tell adaptive cruise control, which is one of the earliest version of autonomous driving technologies, which can help you to determine the speed that your car can go along the way without your involvement, right? So you kind of exchange the driving task between you and the computer, right? In autonomous driving. So I can also talk about parking assistance system as an advanced driving assistance system, which can also help you to safely park your car in a designated area. And autonomous cars, as seen here, mainly rely on sensors, actuators, complex algorithms, machine learning methods, right? Machine learning algorithms. And they have powerful processes to execute behaviors on roads. In this regard, I will give you a little bit more about autonomous cars. They can create and maintain a map of their surroundings based on a variety of sensors situated around them. So maybe at each corner of the car, there are a variety of sensors. They can help receive information in traffic. So based on those information, these intelligent vehicles can do some tasks instead of a human driver. So in this regard, the technology that plays a key role here are many. We have talked about autonomous vehicles, which I will go detail in the sequel. So we have another title, connected vehicles and electric vehicles. Together they form smart mobility. So one question you might want to ask is, connected autonomous electric vehicle is possible? So what type of technology is needed in order to ensure the safety and efficiency as well as higher mobility on roads? So the driver tasks using various artificial intelligence algorithms under different types of traffic participants, such as human-driven vehicles, autonomously driven vehicles. How about that? So can an autonomous vehicle perform its task under a variety of traffic participants, different types? Is it possible? So what type of technology needed to ensure the safety of autonomous vehicles? So as the name states, we will mainly talk about autonomous driving technologies. And first of all, I will introduce some of them here in a part one. Then I will try to blend those technologies in hybrid electric vehicle energy saving. So which is the main objective of the webinar. So what type of opportunities available for us so that we can leverage these driving technologies for hybrid electric vehicles, not just from the safety viewpoint, but also energy consumption viewpoint, right? So there is an unfortunate fact that a big number of people were killed in motor vehicle crashes. These are mainly due to human errors or poor decisions. And it is very common that while driving, you might get distracted. You might be not very experienced in the traffic situation that you are in. So in this regard, these assistance systems can take fully control the autonomous vehicle and can drive. Then it can be a self-driving car. But as we discussed at the beginning, so what do we really need for that? As we discussed at the beginning, we need sensors, complex algorithms, actuators, and machine learning algorithms, so forth. So here I will particularly focus on one type of autonomous driving system, which I call here as a decision maker, right? A decision maker to let the car to make decisions instead of you. For that, mainly we divide this decision-making process into two parts, in higher level and lower level parts. So in the higher level part, this car receives information about the traffic participants, or infrastructure, traffic signs, or traffic lights. And based on this information, using some sort of artificial intelligence methods or control algorithms, it can execute decisions. These decisions can be changing lanes, right? Or accelerating, decelerating. In the lower level, mechanical controllers using actuators perform the task in the lower level as seen. So even though I started from the top of this figure, from environment all the way from top to bottom, but first thing that we need to be aware of that are vehicle dynamics. So we want to control it, right? We need to know the dynamics first, actually. But in this discussion, we are going to be more talking about this decision making as an driver assistance system, driving assistance system. So I just want to give a brief definition of decision making, which is to choose the best solution among several alternatives. In an autonomous driving case, what we need to do using sensors, we receive information and we monitor, observe this information. Probably we don't just do it one time. Since traffic is a highly dynamic process, so we do this at every sampling time, right? At any time of the driving. Then using this information, which I call in car spraying, using some sort of artificial intelligence methods, we execute decisions, right? We accelerate, decelerate, changing lanes, or stop. All these are possible. So regarding this decision making, I don't want it to be a value here. So I will give a specific example. Let's consider a 3 lanes highway driving, and we have several cars, and our autonomous car is seen as red in the middle. So it needs to change lanes because there's a danger in the middle lane, ahead of it. So probably the white car in front of has stopped. So this guy needs to observe the environment and needs to make decisions based on the highly dynamic traffic situation. So how to do this? Mainly, this car uses the relative positions, velocities. At the same time, this guy needs to be in interaction with other vehicles because maybe at a particular time it decides to change lanes, but then it can abort and it can really decide to do other decisions, right? So in order to make this example more clear here, in a traffic situations, we might have human-driven vehicles, right? And we might have autonomously driven vehicles, or we might also have connected vehicles, as seen here. So these connected vehicles basically share information through some sort of communication channels, which I will be talking about that soon. And autonomous car, if it wants to, for example, merge, if it wants to cut in one of the gaps, available gaps in the surrounding, so then it needs to take account all these interactions between autonomous vehicles, between itself and human-driven vehicles, as well as connected vehicles on the road. So there are a lot of things going on. So most car developers, especially autonomous vehicles developers, test their algorithms in real time by driving this type of cars millions of miles to make sure that it is safe enough and it can really prevent accidents instead of creating accidents. So in our case, we test our algorithms in a lab, which I conducted research in this area back in my PhD, and I also continue to work on that. So considering the previous scenario, I derived a human-driven car. So the other cars are connected, and we have an autonomous vehicle, which is the yellow car. So I prevent this guy from changing lanes. Why do I do that? I just want to see the behavior that autonomous car can perform with respect to the other participants' behaviors, right? I can be cooperative or non-cooperative depending on the situation. So what are the challenges? Code, the cybersecurity, of course. For such a system to run smoothly, it requires a big number of lines of codes. So as the design complexity increases, testing and validation becomes more crucial to make sure that everything runs smooth. And cybersecurity, which we will talk about connected vehicles momentarily, cybersecurity is a very important issue because autonomous and connected vehicles are really vulnerable for cyber attacks through communication channels. So without stopping, let us go for connected and autonomous vehicles. So connected and autonomous vehicles combine connectivity and automated technologies to assist or replace humans in the task of driving, as seen. This can be through combination of advanced sensors, onboard and remote processing capabilities, as well as global positioning systems or telecommunication systems. So as we previously discussed, autonomous vehicles use technology to steer, accelerate, and decelerate little or no human involvement. Connected vehicles at the same time use technology to communicate with each other and change state information, for example, in a task of platooning, let's say. They can also receive information with the traffic objects, and this information will definitely help for traffic safety, and it will increase the mobility, right? And the number of these cars, these type connected vehicles, will increase in the future in the world because they are a viable option for human driven cars. And this, some questions, of course, how do we need, why do we need connected vehicles, as we talk about the safety concerns and as well as environmental concerns? We will talk more about that. And the types of, what are the types of vehicular connectivity, and how do connected vehicles communicate, and what are the advantages? As seen in this slide, we have several vehicular communication channels. So one is, let me introduce vehicle-to-vehicle communication channel, which basically exchanges their information between each other. So that's the main idea. And vehicle-to-cloud communication leverages vehicle-to-network access to broadband cellular mobile networks to offer data exchange with each other. So in this regard, vehicle-to-network also stands for the network communication. They can access the vehicular information and maybe change, and the network can share this information with other vehicles as well, right? In a smart mobility case. Vehicle to infrastructure generally refers a vehicle can have information about traffic lights, road signs, so forth. And vehicle to pedestrian, also between vehicle and the pedestrian. Vehicle to mobile, which generally happens through a Bluetooth connection. And vehicle to home, especially for electrified vehicles, a vehicle can access the power management of a house, or vice versa. They can exchange information regarding the battery level and so forth. And why connected autonomous vehicles are important? Because there's a big number of people were killed in the motor vehicle crashes. So this technology is a viable step to increase safety, as well as a greater mobility is a promising feature as well. Efficiency and respecting the environment is another point. And of course, these technologies will also create new job opportunities at the same time. Definitely there are challenges in terms of infrastructure, market introduction. You need to convince people that these cars are safe and efficient, and they are reliable. Also legal issues, traffic management, and decision-making algorithm parts has also different challenges, but researchers all over the world solve these problems step by step. So as we discussed in the first part, autonomous vehicles operate much more efficiently than conventional vehicles, and human involvement with automation, human involvement in driving is reduced. And connected and autonomous vehicles combine connectivity and automated technologies at the same time. And communication, cybersecurity, navigation, collisions, and pedestrian involvement need to be carefully investigated. And so here in the second part, so how we can leverage all these technologies in hybrid electric vehicle energy saving. A brief introduction. Hybrid electric vehicle is a type of electrified vehicle which basically uses two sources of power, and their energy management generally relies on optimizing the power or torque distribution between two power sources. So energy management in this sense in hybrid electric vehicle is basically finding the optimal power split energy sources. In this case, it is an internal combustion engine and electric motor, for example, and the powertrain structure is also given in the here. So how does this work? So we discussed at the beginning that hybrid electric vehicles energy management have been studied from different perspectives. In this case, we will focus more on three main categories: single vehicle, double vehicle, and multi-vehicle case. Single vehicle case then generally considers the external factors like road information, double vehicle and multi-vehicle vehicle cases mostly consider surrounding vehicles and traffic information, route information all together because they use some sort of car following modes like adaptive cruise control or predictive cruise control, which we will talk. So in these main categories, energy management strategies are divided so in single vehicle case, using the information, route information, road slope, and external factors, a power split is achieved from the perspective of minimizing the fuel consumption. But for double vehicle case, the idea of energy management is basically built on the top of car following mode. So what I mean is that in this case, the vehicle A, in this case, vehicle A receives the information of its preceding vehicle, not just for energy savings, but also to maintain a safe inter-vehicle gap. So here, we consider a situation where this vehicle A and B are connected. Right? They exchange their information through a communication channel. It might be vehicle to vehicle in this case. At the same time, let's say these two cars receive information about infrastructure, right? Traffic light signal times, for example, traffic light state, as well as information through these channels, information of the preceding vehicle, such as speed and acceleration. So once those informations are available, using a proper objective function, we can determine optimal power split considering the traffic environment, right? Traffic interactions. So why this is promising? This is promising because we just don't optimize the energy management for a single car. So we do that for double vehicle, maybe more, multiple vehicle cases, which I will show in the sequel. So there are two strategies available for double vehicle case. First one, adaptive cruise control base, which basically tries to maintain a inter-vehicle safe gap. At the same time, determine a good, the best power split in the powertrain level. The second option, which is available to us in the literature, is predictive cruise control. So this predictive cruise control mainly obtains mainly predicts the preceding vehicle velocity or acceleration up to a certain horizon, and using those predicted values, follower hybrid electric vehicle can determine its optimal velocity as well as optimal power split up to a certain horizon. So using this prediction, the algorithm can be more robust to driving cycles, and changing conditions in driving can be better captured. So multi-vehicle case, which I show this figure maybe in one longitudinal direction, but it can be extended to lateral case as well. So maybe these cars are also changing lanes altogether, right? In a truck case, let's say. So the communication devices such as vehicle to vehicle and vehicle to infrastructure and pedestrian, all these considerations are needed. They need to be taken account carefully for multi-vehicle case, because we want to optimize a global power energy consumption in this case, such that vehicles, connected hybrid cars can travel safe and they can minimize their overall fuel consumption. So a control algorithm that can take into account all these factors need to be carefully designed. And as we discussed energy management strategies in the previous slide, so energy management strategy in this case, considering the external factor, factors, as well as considering the dynamic traffic changes, they can find optimal power split. So here we can design a control algorithms, but considering all these details, we cannot design a control algorithm considering all these details under one roof. Maybe we might need to split the problem into several sub-problems and try to integrate each part, which cannot be really easy, but it is a really promising problem to solve a big problem here. So what to really take away in today's presentation, we talk about vehicular connectivity, how they can be achieved through network channels, communication channels, and these informations are really useful not just to follow connected vehicles each other, but also to determine their power split, their power management at the same time. And of course, designing these algorithms requires several considerations at the same time. But what is really promising, available autonomous driving technologies, available research allows us to apply this in a hybrid electric vehicle energy saving, so that a global optimization can be achieved. Here, I want to special thanks go to Complex Engineering Systems editorial office for organizing this webinar. And regarding my presentation, I will be happy to answer your questions in the question and answer session. Thank you very much.
Thank you very much, Dr. Coskun, for this excellent presentation. This is a very challenging topic and very interesting. So I hope the audiences can come up with some questions in the Q&A, the time slot. So thanks, Serdar, and then we can continue with the speaker.